Okay, welcome back. So hopefully everyone had a good Thanksgiving break. So today we're going to start with continue with MRI, lecture 6. So logistics wise, we are in week 9. So there's this week and next week, and then project 2. Everyone knows is during final exam period. So I think the project proposals are due this Wednesday, right? And so just as they come in, you'll get feedback. If it's okay, you'll be approved right away. If you need to revise it, there'll be comments on how you should revise your proposal. Then you need to resubmit it. So that's any questions on the project 2 proposals? Okay. And then yes, go ahead.
Yeah, I have a question. What exactly do we have to include in the project proposals?
Basically, you need to provide at least a few sentences describing what you'll do. And if there are papers you will cite, I think I would suggest rereading the project 2 assignment. And then if you don't provide enough information, then I'll give you feedback.
Okay, got it. Thank you.
It should be pretty clear, like if, for example, if you just submit a proposal, say, we're going to discuss these papers, that's not really sufficient. You need to say what exactly you're going to do. So it's almost like an abstract of your proposal, of your project. Okay. Any other questions? Yeah. So does that answer your question? Okay.
Yeah, thank you.
Great. And then project 1 scores have been finalized. So those will be posted later today. So maybe Mara Luz, if you could remind me, or if someone in the room or on Zoom can remind me, I will go over sort of the statistics of that at the end of the lecture. So just someone remind me to do that. And right now we're just basically, I'll discuss a little bit about that at the end of lecture today. Okay, so just someone remind me if I forget to do that. Okay, so are there any questions about course content or homework 5 that's sort of you're working on now, or maybe, yeah. So I've noticed people have actually solved all the MATLAB grader problems, so I know they're doable. Yes, question.
Number 4 for the square spiral, when we're graphing them,
yeah.
You want like a GX y versus time?
Yes.
Like GX versus GY or GX?
GX and GY both individually versus time.
Both.
Yeah, and then KX and KY individually versus time. I mean, you can always add more. I mean, it's useful to plot KX versus KY just as a sanity check, because your answer should look like the square spiral, right? So that's a good sanity check, but that's not required in that homework. Okay, any other questions before we start? Okay. So today we are going to review a little bit of what we did last time, since that was a long time ago. So we're going to do least squares and minimum norm solutions. We're going to get into parallel imaging, compressed sensing, deep learning, and if we're lucky, we'll get to relaxation. Okay, so we'll see how far we get today. Just the pre-lecture quizzes are very useful for me, at least, to see what people are getting confused on. So just to reiterate, if you're talking about aliasing, that has to do with the field of view, right? And so typically, the constraint is delta K has to be less than 1 over the field of view. Okay, so that means if you're seeing aliasing, it means you haven't satisfied this constraint, so your delta K is too big. Okay, so anything to do with aliasing is your delta K samples. All right. Now resolution, on the other hand, is the resolution. It's your width has to be 1 over the resolution. Okay, so if this resolution gets this is sort of, maybe that was the problem with the question. I think, did it say higher resolution or something? Okay, so higher resolution typically means delta X is getting smaller, right? So then you want, so like, and we all know this, right? If you buy a high resolution camera or a higher resolution monitor, you don't expect to have fatter voxels, right? So delta X doesn't go up with higher resolution, all right? So I think we all know this. So just remember, higher resolution means smaller delta X. And it makes sense because that means your width has to get bigger. You've got to go out farther in Fourier space, all right? So just remember, resolution means you need higher spatial frequencies. So higher resolution, higher spatial frequencies, okay? And then there was one thing about the dephaser. The dephaser refers to this. This is the readout dephaser here. And you notice this has to basically take you out to this point in case space, right? Okay. So it turns out the equation for solving is exactly the same equation as what we use for the phasing code, except you used the FOV of X and FOV Y. So because this, remember, this one had to get you halfway out in the KY space, right? And so actually, if you just apply these equations, you would get the right answer. So it seemed like a lot of people, majority of people got the right answer, but other people were off by a factor of 2 or 1/2, okay? So remember, you're going out to this part in case space. You're not doing the whole case space. So the job of this one is just to go halfway out in case space, right? And I think the other problem, most people got that right, so I don't think we need to go over that. So any questions, either in person or online? Okay. So let's review where we're at. So what we've covered mostly in the class is up to circa 1983, and we're working our way up into the late 90s. This is basically, if you go and get an MRI exam today, highly likely you'll have one of these done for you, okay? You would typically, especially at UCSD, you'll always be scanned with a multiple channel coil. It will essentially be doing some sort of acceleration to go faster, okay? You might have some compressed sensing, although that's not as prevalent. And you might have some deep learning, and you might have some simultaneous multi-slice. So we're not going to be able to have time to go over all these. I noticed there is a project on MRI fingerprinting, so we'll find out about that in the project. So we're just going to we'll spend most of our time today on the parallel imaging, because that is sort of bread and butter right now. And we'll touch upon compressed sensing and deep learning, simply because those are sort of around. Although the sense is that deep learning may overtake compressed sensing at some point, okay? Okay, so just to remind you of what we talked about last time. Typically, we've talked about, we have an object and we do a 2D Fourier transform, right? And so everything is in 2 dimensions here, nx, nx and ny, nkx, nkky. So what we want to do we want to express this as a matrix equation, okay? So we need to take this square object and convert it into a vector. So this is like a matrix, right? And so we just take it column by column and make it a vector, okay? And similarly, we can do the same thing here. We take this matrix and make it a vector. And then it turns out that the 2D Fourier transform is simply, we take some, depending on where we are in case space, we just fill this row with this complex exponential, okay? We multiply it by our image, and then that gives us the value of the case space. And so this actually should be capital M, okay? Let me just change the color on that. Okay. So basically what I just said, we vectorized those matrices such that we now have the signal we measure is equal to the object we care about multiplied by encoding matrix. And so now everything becomes in the realm of linear algebra, all right? Okay, so the simplest thing is obviously if the number of equations is equals number of unknowns, it is equal, this is a square matrix, right? And then assuming this is what's called full rank, right? You can take the inverse of this, all right? And that is essentially the 2D Fourier transform, okay? So this way is the Fourier transform, this way is the inverse Fourier transform, all right? So that's the matrix interpretation of Fourier transforms. The next step, as we talked about, is overdetermined system equations. And so this is where you have more equations than unknowns. And so you're not necessarily going to have a solution, right? There may not be a solution that actually satisfies this, okay? So what you have is the least squares estimate, which minimizes the error between what you measure, S, and what you predict, E times M hat. All right, so most of you are familiar with that. And then obviously we can have the underdetermined set where there's less equations than unknowns. And here we end up with the minimum norm estimate. And so the idea is, as you remember from high school or grade school, basically when this is the case, there's there's infinite number of solutions, right? So you have to pick one, okay? So one of them you can pick is the minimum normous estimate, which is just the estimate that is the smallest. If you think of it as a vector, it has the smallest length, okay? But as we'll see, that isn't the best solution typically, okay? So the trick is behind parallel imaging, compressed sensing, and deep learning is how do you go from this solution to a better solution, okay? Because we know this solution is what gives you aliasing, and we don't really want aliasing in our image, all right? Okay, so just to remind you, this is all enabled by the fact that now modern scanners have multiple channels and the coils have multiple coils. And so we're going to talk a little bit about how you design those coils, like what's the optimal way to design those coils, okay? And on your next pre-lecture quiz, which will be posted today, there'll be some questions where you have to think about, which coils have the best performance, okay? Okay, so let's just review a little bit of what we talked about last time. The simplest thing you can do, obviously, is you have a bunch of coils. You can still have each of the coils have a full square matrix associated with it. So this is, you're doing full Fourier transform. You're acquiring all the data you need. You're satisfying a Nyquist condition, okay? In which case, any one coil can reconstruct your image, okay? But you notice each coil here, so these are representing where the coils are. Each coil is going to be brighter. The image is going to be brighter close to where it is, okay? So this has a coil sensitivity. So if I zoom in on this, you can sort of see this coil here is bright here and falls off. This coil here is bright here and falls off, okay? So the first question that people had to ask in MRI, and this was in the early 1990s, was if I have this and I'm doing a full Fourier acquisition, then how should I best combine these coils? Okay, because basically I have more equations than unknowns, and what's the best way to combine all these coils? Now, any one of these is fine, but as you can sort of see, they have the problem that they're bright in one area and dark in another area. So I'd like some way to combine those, okay? It turns out, just to remind you, the answer is actually simple. Let's say I have two coils. So this is one coil, this is the other coil. What do? I take this image, take its magnitude, and I square it. I take this image, this is a magnitude image, and I square it. And then I add them together and take the square root of the sum of squares. So that's what SOS is, square root of sum of squares, okay? And I get this, okay? And it turns out that's pretty close to the ideal if you solve that big matrix equation. So in general, people don't solve that big matrix equation in this case. You just reconstruct every coil's image and you do the sum of squares, okay? And then what we'll see is later on, we'll see this come back when we're looking at some parallel imaging. Okay, so that's sort of a review of what we did last time. Now let's sort of get into where we sort of left off, which is aliasing, okay? So remember, ideally, if we satisfy the Nyquist conditions, then this is a square matrix, right? My delta K is correct, my width is correct, and I get a nice image. If I acquire this data, I get a nice reconstruction, okay? But let's say I just throw out every other KY value, okay? Then what that does is I'm essentially throwing out every other row here, okay? I'm not acquiring that data. And so this is going to go from a square matrix to a rectangular matrix, which has less equations than unknowns. And so this has infinite number of solutions, right? The solution that if I just solve this, this is what's called the minimum norm solution, which is exactly the same solution you get from our Fourier theory, which has aliasing, okay? And so the idea is essentially, this is the solution that assumes that all the components that I did not acquire are zero, okay? So for example, this image here has some component that varies with that sort of variation, right? There is some variation across the image, right? But I assume that that's equal to zero here, right? So now this image cannot have any variation. So the most it doesn't have a low frequency variation to it. So that's why this appears here. Okay, there's not enough information to get rid of this component. All right. So that's how aliasing appears. You're basically just missing information. And so the algorithm does its best to say, well, given what you found, this is the best I can do. Now, this is not the best solution, right? You can do much better than this if you make some assumptions, which is what we're going to see. Okay. So the two approach, so let's remind ourselves. So this is what we want. Now, one way we could go, so the idea in MR is it takes time to acquire all these scans, all these KY lines, right? And so we always, to go faster, we've got to acquire less data in K-space. Okay, so that's the whole name of the game, is how do I spend less time in K-space? Because that's where I'm collecting the data. So one way is I don't collect these outer lines, but that means I'm windowing and I'm not acquiring these high spatial resolutions. And so that's going to lead to lower resolution. Okay. And that's not always desirable. What you like is this, just as good as this, but twice as fast, or 3 times as fast, or 4 times as fast, right? You want to get the same image, but just faster. So the other approach is you could skip every other line, which we just talked about, and that gives you the aliased image. Okay. So parallel imaging approach is saying, well, how do I go from this undersampled acquisition? I say, well, if I have a lot of coils, then every coil basically sees, it would be aliased. But since I have multiple coils and multiple signals, I go from this underdetermined system back to an overdetermined system. So you use the coils to make up for, your lack of data in K-space. Okay, so there's a trade-off now that you can make. And the question is, how should you do this such that it looks better and it works robustly? Okay. So what we're going to talk about, and I'm going to sort of, for most of this, for this material, I'm going to mostly give you sort of the intuitive understanding of how it works. I'll go over some slides which show the math, but you're not responsible for that math. You're responsible for intuitive understanding of what's going on. All right. So make sure, for those of you who are live, to take advantage of this and you can ask questions. Okay. In parallel imaging, we have the acceleration factor R equals 2. Okay. So when you see acceleration factor, this means sort of how much faster you want to go. Okay. So if I cut out half the lines, then I can go twice as fast. So then R would be equal to 2. All right. So that's, in this case here, R equals 2. Siri is trying to respond. Go away, Siri. Bye, Siri. How do I get it? Okay. All right. So now EU is this n by 2 by n undersampled Fourier transform. Okay. And it can be written as actually concatenation of 2 sort of n by 2 by n of 2 Fourier transforms. So basically just smaller Fourier transforms. So the key is to get rid of that, I can go and solve this big equation, okay? But the problem is this equation, if you think about it, let's say I have 30 coils, okay? And then I have 256 by 256 image, okay? So n squared is on the order of, what is it? What's 200 squared? Like 40,000, right? Is that right? No, it's 400,000, is it right? Wait. 40,000. Okay, so I have 40,000 by 40,000 matrix, and then I multiply that 30. So then I have like 40 times 3 is 120, 120,000. Wait, I have 40,000, and now I'm at like a million, right? A million rows by 40,000 columns, right? So MATLAB, if you put that into MATLAB, it's just going to spin forever or just say, I can't do this. Okay. So that's not a solution. So it turns out some really smart graduate students in the late 90s figured out how to do it better. Okay. So what we're gonna spend most of our time is going over what's called sense recon, which was invented. I think the story behind this goes, they had seen some results at the annual conference and were thinking, well, there must be a better way to do that. So I think they were on a boat somewhere, rowing somewhere on a lake, and they figured it out on the lake. And this is very common in science, where the answer actually never comes to you while you're like grinding away in the lab. It usually comes when you're grinding away, after you've grinded away for a while, and then you're out in nature. Or I remember one time in grad school, I was like just washing the dishes. I was like, that's the solution. Okay. So you want to make sure, especially if you're doing a PhD, make sure you have enough downtime so your brain can sort of do the subconscious sort of deep neural network pruning and learning. Okay. So it's not to say that you can don't get the impression you can vacation all the time. That doesn't work either. You got to work hard, but you also have to make sure you have downtime. Okay. That's where all these connections get made. And that's where a lot of these, in science, it's called the eureka moment, where you're like, that's the solution. Okay. Okay. Anyways, yeah, so let's see. So the signal, let me see what this is. Okay. So let me just say that we're not going to go through this slide here too much. I'm just going to tell you that, just remind you that typically, as you saw in spin warp, we acquire line by line by line. Okay. So going across the line is pretty quick, right? So there's really not much gain. Like we can typically do that in like a few milliseconds. Okay. So there's not much gain in accelerating in this direction. What takes time is acquiring line by line by line. So typically we're going to accelerate along the dimension that's the slowest. And so that's going to be the phase encode direction. All right. Okay, so let's work through an example so this slide we're going to work through and sort of derive, the sense algorithm. Okay. And so here's the idea that if I have an image here, right, with let's say two voxels, and these are FOV over 2 apart. Okay, so they're half an FOV apart. Okay. So these two voxels, if I acquire a full Fourier image and I acquire it with some coil and I reconstruct it, then I get a nice image that just is sort of shaded a little more towards the coil. But I can resolve these two, right? Because I have all the information in Fourier space. Okay. But let's say I did that same thing and I cut out every other line in K space. So now I'm going to have aliasing, right? So point A and point B are going to lie on top of each other because things repeat at FOV over 2 now. Okay. So now this has got this image here. Let's say this is the image from coil 1. It's going to have some sensitivity. So let's say this is the coil sensitivity of IA. Okay. So this is, let's see. Yeah, CA1, right? So that's the first coil, plus CA2, no, sorry, CB, sorry. Okay, it's just saying that IA and IB are what I care about. I want to know these image intensities. So the first coil multiplies it by some coefficient CA1, and this should be CB1. Okay. So that's just saying there's a sensitivity at A and a sensitivity at B, and this is for coil 1. Okay. And then I can write, now that I've got that, the rest should be easier. I have CA2IA plus CB2IB, right? And you see where this is going. F3 equals CA3IA plus CB3IB. And now F4 equals CA4IA plus CB4IB. Okay, so I've got 4 equations, 2 unknowns, should be okay, right? So let's rewrite that as a matrix equation. So what I measure are these F1s, right? I measure F1, F2, F3, and F4. What I want to measure, I want to estimate IA and IB. And so what's in here? Okay, well, I've got CA1, CB1, right? CA2, CB2, CA3, CA4, CB3, CB4. Okay. So it turns out that this is actually what's called Whoops. What happened there? Okay, this is the sense algorithm. Okay, this is exactly, if you are required to scan, and a lot of scans use this, or some version of this, then this is essentially, for every voxel, it's solving this equation. So it actually takes, yes, go ahead.
That's what the F stands for.
Oh, the F is just the variable for like the image. The whatever you so basically, if I reconstruct this image here, it's just the value of that image at that location. Yeah, so F1, F2, F3, and F4 are all the same voxel, and they're just the value that coil. So F1 just means coil 1 measures that signal. Okay. Coil 2 measures that signal, coil 3 measures that signal, coil 4. And each of these is aliased, right? So you have two things on top of each other. So the unaliasing is how do you tease that apart? All right. So that's the sense equation. And so it turns out that you've taken this huge matrix equation and boiled it down to a bunch of very small problems. Okay. Because this is a relatively small problem that you can solve. Okay. So essentially, this is just doing this in nicer form. Okay, but we get the same solution. Right. Okay, so this slide I'm just going to zoom through. Basically, it's just showing that if you want to solve this equation, like for two coils, you can sort of break it into this least. It's still the least squares estimate. And now the trick is, how do you write this big least squares estimate, which looks sort of wonky, into, it turns out there's, with a lot of tricks in algebra, you can take this matrix and break it into little equations. And each of these little equations, it's this block diagonal form. So that's where the sense algorithm comes out. You're just solving these like little linear systems of linear equations. Okay. So that's basically what the sense algorithm is doing, is taking this matrix, and this is quite common in especially EE signal processing. You have a matrix that is really hard to solve if you solve it without noticing the structure, but if you rearrange it, all of a sudden you can break it into lots of smaller problems. So a lot of stuff that we depend on every day in our in our phones and our computers is just really smart people going, this is going to take forever to solve if I solve it in its native form. But if I rearrange it, I can break it into smaller problems, which are cheaper to solve. And basically, that's why GPUs work really well, right? Because essentially, GPUs are really good at solving lots of problems, small problems individually, right? So sense is essentially a way of doing that, where, for example, that's why sense works really well if you have a GPU, because you basically can solve all these individual problems simultaneously. Okay. Okay, so basically the idea of sense recon is, because of the structure of matrix, the larger system of equations can be broken down into a set of smaller problems where each is just a solution to a fairly small linear system of equations. Okay, so that was the key insight behind sense. That was, I think, published in 1999. Okay, and it basically changed how people did MR like immediately. Okay, so we're going to spend some time looking at how sense recon works. And this is for the current homework, this is the code that you'll be playing around with. So we're going to spend some time going through what it looks like. And then your job is to play around with these coil profiles and come up with some new coil profiles and look at their properties, okay? But the code is all there, so you simply just have to change the definition of the coil profile and then comment on what you see. So it's really meant to sort of just guide you. It's like a guided exercise, okay? But let's go through it, because there is some pretty important intuition that we want you to develop about parallel imaging, so that when you go, and if you do go into MR, when people talk about parallel imaging or something called G factor, at least you have some sense of what they're talking about. Okay, so let's assume we had two profiles, and let's assume this is in the Y direction. So one coil is very sensitive here and then drops off, and this coil is very sensitive here. And so they're sort of complementary sensitivity patterns, right? Each coil sort of sees its own part of the object. So if you look at this coil profile, it's very sensitive here, drops off here. This coil profile is sensitive here, but drops off here. So if I had a square object, which I'm not showing, it would look like this, okay? So it's bright, but falls off. This is bright, but falls off. And now here's the thing. I add some noise and I do an undersampled recon, right? So the undersampling is going to give me aliases, right? So now I have an aliased image, and also it's got some noise added to it. All right. So the idea is that how do I go from these aliased images? And if I do, and in the code, because it's such a small problem, I don't have to actually do the little trick of the sense recon. I can just solve the equation very quickly, right? I can just do the full inverse, all right? So that's what's in the code. And so if you do that, this is the image you get, which looks pretty good, right? It's basically undone the aliasing. It's gotten rid of these, it's added these up correctly, and you get a pretty good image. Okay, and it's a noisy image because you've added noise, so that makes sense. This is the best you can do, actually. Yeah, this is the least squares estimate given these two coils. All right. And there's something called G factor. And I just want you to notice the scale. This G factor average value is around 1. Okay. And that's the ideal would be 1. So we're doing pretty well. We'll talk about what G factor means in a minute, but just for now, just showing you that in your when you run that code, one of the plots is G factor. And that's something you're going to want to look at when you're designing your coil profiles. All right. So now let's look at a different coil profile, which we've looked at before. These are two coils which pretty much see the same thing, right? They're just a little bit different, but they essentially both see the entire object. And so if you look at their 1D profiles, they look almost the same. They both do a pretty good job of seeing the object, right? With a little bit of shading, but it's hardly noticeable because there's only like a 10% reduction across the field of view. And if I do the undersampled recon and add some noise, I get these aliased images with some noise. But now the problem comes when I try to do my recon, my sort of least squares estimate, this is what I get. And so I get a really crappy looking image. Okay, even though I've solved the equation perfectly, this is the least squares estimate, this is the best estimate. Okay. And if you notice this G factor, now this scale is around 18. Okay, so I've gone from about 1 to 18. So one thing to remember is bigger G factors means bad. Okay, so if you see a G factor, and typically anything a G factor over 2 is typically not a good coil. Okay, so what this means is now the RF designers actually have to, you can't just be like, if you're in the old days, if you were an RF designer, you would just say, okay, I want to design a coil that has really nice homogeneity, gives me nice electrical properties. Now the coil designers actually have to take into account the reconstruction. Okay, they have to say, okay, well, how would this coil work with the reconstruction? Because obviously, if I design a coil like this and gave it to my manager, it would just, and then these are the images that come out, they would say, well, this coil sucks, right? Go design a better coil. All right. So now you're seeing the construction of the hardware depends on the recon. So there's this interplay between the two. Okay. So let's talk a little bit about why that happens. Okay. So let's say we can go back to this sort of simple linear thing. We're just estimating two things, IA and IB, right? So basically we can say what we measure is just the sum of these two vectors, this vector and this vector multiplied by different coefficients, right? So let's call this vector 1, let's call this vector 2. So I'm just saying that what I measure, and there's going to be some noise out here, okay? It's going to be IA times vector 1. Let's put the vector on that just to make it clear, plus IB times vector 2 plus some noise, okay? And then let's say, this is also a vector, okay? All right, so let's draw out two sort of scenarios, okay? So since I only have two vectors, I can think about things in a two-dimensional vector space, right? Those two vectors just span some plane, so maybe let me change the colors here and do that. Okay, so let's say let's take the case where V1 and V2 are very similar. V1 and V2 are very similar. Okay. And then the my F vector does not have to lie in that two-dimensional space because it's a four-dimensional vector, right? So the F vector could lie out here. Okay. And then the least squares estimate, remember, is I'm projecting on to this and trying to find the best summation of those two that gives me that least squares estimate, right? But let's say I have some noise here, like I have a noise bubble here, right? Like noise, the vector could be anywhere. That F vector with noise can just point somewhere in some like sphere, right? It can vary around. So when I project it on, I can imagine it's projecting onto some circle of noise, right? So let's just look at the two-dimensional plane. So if I have let's say that projection is here, and it can be in some vector here. And then I've got these two vectors, v1 and v2. Okay. So you notice that these two vectors are very similar. If I end up, if the noise puts me over here, okay, the best fit is going to be something that's closer to v1, right? But if the noise points me over here, the best fit is going to be v2. So my estimate is very sensitive to the noise. Okay. So that means if those two columns are too similar, then my estimation is very sensitive to noise. That's the high G factor. Okay. Whereas think about it this way, let's say V1 and V2 in the best case are orthogonal, V1 and V2. And let's say I had some projection here with some noise on it, right? Okay. So now even if I move along to these points, the summation of V1 and V2 that gives me that is going to still be some combination of V1 and V2, right? So if I think about, so this is going to give me a better estimate of these coefficients, right? Because I'm looking for the coefficients that add up to this vector, okay? So in this case, I can think of this taking, like, let's say I take a point here, it projects onto here and here, right? And if I take a point over here, it projects onto here and here, okay? So I'm still, the uncertainty is a lot less. So this is sort of my uncertainty and my estimate is pretty small when those vectors are orthogonal, right? Whereas if I make V1 and V2 very similar, right? And I have some uncertainty and I project onto that, then I'm going to flip between V1 and V2, okay? So that's what you're seeing. So that's why the coil design is always trying to make these vectors as orthogonal as possible, okay? Or as different as possible, okay? The more similar those are, as you'll see in your homework, then that's what causes the noise amplification, all right? So let's take a look at this case here on, so this, let's look at this vector here. So now we just have two, so let's look at what that looks like here, okay? So remember the F vector is just sort of, and let's say we take 2 points that are f of e of 2 apart. Let's say these are the 2 points we look at. Okay, so this is point A, this is point B. Okay. So remember the rule of thumb is I take coil 1, let's say this is coil 1 and coil 2, and I take its values at A and B. Okay. So coil 1, let's say, is 1 and 0, and coil 2 is 0 and 1. So those are pretty orthogonal, right? Just looking at that. So that's going to give me very good reconstruction, right? Whereas this one, if I look at this one, let's look at the F vector here. Let's take those some points A and B. So eyeing it, I get about, let's see, at that point, it's like maybe, let's say it's 0.97, maybe 0.92 or something. And then vice versa, it's probably the same. It's 0.92, 0.97. Okay, so those columns are very similar. So then we're going to get much more noise amplification, right? So when you do your homework, just play around with, how you set up the coils, be sort of creative and play around with different coil profiles, all right? But that's the basic intuition we have. So I'm going to sort of just jump over these. These just sort of tell you how it's defined. And the G factor is essentially what is the SNR when you've done your parallel imaging versus what it is if you did full Fourier, where you acquired all the data. And this is the penalty you acquire. So there's a square root of 3 because you're acquiring less data, but the G factor, you notice here, the bigger G is, that means this SNR of your parallel imaging goes down, okay? So ideally, you want to make G equals 1, all right? And so this is showing you essentially for an image where we're seeing that the coil spacing, so basically, in this case, we've acquired the same image, but here we have 2 coils, and going from left to right, they're spaced 1 centimeter apart, and then we increase the spacing so that they see different parts of the image. So we've gone from 1 centimeter to 3 centimeters to 6 centimeters apart, okay? And as you can sort of see, as we spread those coils apart, the image looks a lot better with noise, right? And if you look at the G factors here, this has G factors of about 5. The G factors go down, and then here, I'm down to close to between 1 and 2, okay? So if the coils see the same thing, basically that's not good. So there's the part of our coil design is how do you get the coils to be sort of, they see sort of the same thing, but just in a small region. And so you have these overlapping coils that see enough, there's enough overlap, because if there's no overlap, neither coil sees anything here, then it can't reconstruct that. So there has to be enough overlap so they sort of see some of it, but they can't have too much overlap, okay? So basically that's the G factor, and it turns out that it involves, this parts of this matrix. And the bottom line is the more similar the columns are, the higher the G value. Okay, so that's what that computation comes down to. Okay, so this is the computation that's in your code, so you can look at that if you want to. And you can sort of see it's making use of those columns. Okay, so, and then this is the G factors. You can sort of see here across the profile, they're going between 1 and 1.2. So pretty nice G factor. For this coil profile, they're around 18, which is a lot of noise amplification. Okay, that means your SNR has decreased by a factor of 18 by going from a good coil to a bad coil. Okay. Okay, so any questions on that before we switch gears? Okay, so hopefully that should be sufficient to help you get through, I guess it's problem 5 in the homework, is that right? Okay. Okay, so the next thing we're going to talk about is a slightly different kind of parallel imaging, which is actually in some ways overtaken sense because it has some nice features to it. It's called GRAPPA. Does anyone know what GRAPPA is? Okay, so I've never had it. It's an alcoholic drink, obviously made out of grapes, popular, I think, in Eastern Europe. So if you enter MR, you'll see a big part of MR is coming up with good acronyms, and so GRAPPA is a pretty good acronym. Okay. So here's the idea behind GRAPPA: is for sense we've thought about everything in sort of solving these linear systems of equations, right? And we're like, okay, how do we solve? And then we sense the genius behind sense is it took this big linear system equation and broke it down into lots of little equations. GRAPPA has a slightly different approach, which is also sort of ingenious, which is it's based on this insight. Let's say I have this this is my object and it's this Fourier transform, right? And let's say I see this object through a coil that has some coil sensitivity, right? So I'm essentially taking this object, multiplying it by something that has a very spatially varying sensitivity, and this is the image I get. Okay, so this obviously has a big effect on the image I get. Okay, so now let's look at what that means in the Fourier domain. This is the Fourier transform of my object. I multiplied in this domain by this sensitivity pattern. So I'm going to convolve in the Fourier domain with this, the inverse transform, or the Fourier transform of this sensitivity pattern. Okay. And the smaller I make that sensitivity pattern, the broader that kernel is going to get, right? So now I take this and I convolve these together, and now I end up with a blurred out version of my original Fourier transform. What that means is points in K-space are no longer independent, right? Our assumption was we have to acquire every point in K-space because it's giving us unique information, right? But once I've done this blurring, guess what? This point in K-space is actually a summation convolution of all the stuff around it. So I don't actually have, like this, you can argue that here, maybe I have to sample every point in K-space. Here, there's a lot of structure to this, so I shouldn't have to sample this as much. And I should be able to undersample it, and then figure out what I didn't sample, okay? So I'm going to interpolate in K-space. So for your pre-lecture quiz, the intuition is think about what happens as you make a coil sensitivity pattern smaller, then remember that kernel gets broader, okay? Which the broader that is, it means that your assumption of doing GRAPPA is better, right? Because if that kernel, if the sensitivity pattern is very big, right, then its Fourier transform is going to be very small. So then the assumption of GRAPPA is going to be less applicable. All right. Okay, so here's how GRAPPA works. It's pretty cool. It's basically what's called a self-calibrating method. Okay, you are going to acquire some scans at the beginning where you actually collect full Fourier, at least in some region. Okay. So you might, at the beginning of every GRAPPA scan, there's going to be some calibration images where you actually acquire all of Fourier space, okay? So I acquire all of Fourier space, and then what I say is, well, I've acquired all this data, okay? But eventually I'd like to not to have to acquire this point, okay? So I need the weights that allow me, let's say I want to not collect this point, and I want to, these are along the coils, this is along K-space. I want to estimate this point in K-space based on some linear summation of these other points, okay? So we use the calibration scan, where we know the data, and then we use that to calculate the GRAPPA weights, okay? So essentially, we do a pre-calibration, we figure out the weights, and then we use those weights for the rest of the scan, okay? And so so basically here, now notice all these zeros are where I don't acquire any data, and I'm going to fill in the data here based on these weights. Okay, so that's the idea behind GRAPPA. And then each of these is now a full Fourier acquisition, right? So I can reconstruct each of the coils images, and then I can do a sum of squares recon at the end. Okay, so basically it's a sort of a cool way of looking at the problem in another domain. Turns out there's sort of an interesting GRAPPA and sense obviously have to be related, right? And so, but it's sort of a complex to go into that. So we're not going to go into that. Okay. So for example, let's look at this example here, so the question is, which one of these would be better for GRAPPA, right? We already said that this is going to be better for sense, right? Because this gives me two different columns, two fairly independent columns in that matrix, whereas this gives me columns that are too similar, so I get a lot of noise amplification. Turns out that this is also better for GRAPPA, right? Because each of these is narrow, so it's going to have a pretty broad Fourier transform. So there's a lot of smoothing in K-space. So the assumption that I can predict this point from its neighbor points is better than if I look at this. This is almost just flat. So in the limit, it would just be a delta function. So then neighboring points in K-space don't really tell me much about this point. So I can't really predict it very well. Okay. So it turns out that luckily what's good for GRAPPA and sense, what's good in parallel imaging in general, tends to give you the same design. Okay, to the first order. So here's the idea behind GRAPPA. Essentially, we take this problem here, okay, and we essentially take so these are the undersampled images we acquire. So each of these is undersampled, and we take each of these and we make it such that we go through the GRAPPA recon and we make it each of these essentially the full Fourier. Okay, so essentially you can sort of see we're doubling the size of these vectors, and then each of these we can reconstruct using our overdetermined set of equations And so GRAPPA, we interpolate in K-space, so we get the full Fourier. We reconstruct the image for every coil, and then we do a sum of squares recon. Okay, so that's how GRAPPA works. And this is how GRAPPA looks. So basically, this is RF2, RF3, RF4. So here I've gone twice as fast, 3 times as fast, 4 times as fast. Okay. And here I've gone 3 times as fast, 2 times as fast. So you can sort of see here that there are things that start appearing. So if you look here, like this part of the image, right, it's starting to look a little more grainier here, right? There is a little more noise amplification because sort of the, you're acquiring less data, and also sort of the assumptions of GRAPPA may be falling apart. And you can sort of see here, it really is falling apart quite a lot. Okay. So in this part, because probably the coils aren't set up correctly, you're just getting a lot more noise amplification. And so the trade-off as an engineer or a physicist is you're always trying to figure out what is the fastest you can push, right? So, for most radiologists, they would not be happy with RF=4. So you really couldn't sell that as a product. You get a lot of complaints. RF3, you might be able to get away with it, in certain applications, but probably they would recommend RF2, because then you're going to get the less number. You're going to minimize the number of complaints you're going to get from the field. Okay. Similarly, if we look at here, this is RF2 of GRAPPA and RF3 of GRAPPA. Let's see, what are they pointing out? You're starting to see this structure you're seeing pretty well here. You're starting to see things not as well, and you're sort of seeing maybe even some artifacts. Like this is probably an artifact here now. Okay. So that's the name of the game in MRI recon is, as you develop new ways of doing the reconstruction, you also find new artifacts and things that you have to deal with. Okay. And so it's always a trade-off between, yeah, I can go faster, but I have to make sure I don't introduce artifacts. And especially with deep learning, I think most of you are familiar with like the hallucination issue with deep learning networks. You certainly don't want to introduce things that don't exist, right? Like if you have a deep learning recon and it introduces tumors where none exist, then you're really in trouble. Okay. So we'll talk a little bit about that as we go on. Okay. So just to summarize what we've talked about here, and there's a nice, for those of you who are interested in this, there's a really nice review article in IEEE Signal Processing Magazine 2020. So that's where this figure is taken from. The idea is just reminding you that we can either do sense recon, okay, or we can do GRAPPA. And so these are sort of the 2 main paths we've talked about, okay? Okay, so any questions before we switch gears a little bit? Okay. So now we're going to talk a little bit about sort of what I would characterize as sort of a paradigm shift. Up to now, we've assumed that we've made no assumptions about our image, right? We're saying we need to get the best answer possible given our data, and I have not assumed anything about my image, right? I'm just trying to do my best to reconstruct it based on the data. But think about it this way. The space of all possible images is actually pretty huge. Like for a 16-bit image, I have 1 billion possible 120 by 20 images and 17 billion 512 by 512 images. That's what I would have to read. That's the sort of the universe of all images I have to be able to account for, right? Or if I have a 32-bit image, there's 70 trillion possible images if it's 128 by 128, 1 quintillion images, okay? So it's up to now, we've been working on a recon to sort of cover that entire space of possible images, which is a huge space, right? But that space includes images like this, right? Which are clearly not, like, without even being a radiologist, you can sort of say, well, those are clearly not biological. Those are maybe biological, but they clearly have artifacts, right? So the actual space of actual biological images is actually much smaller than the total space of all possible images, okay? So what we're going to see is what compressed sensing and deep learning are trying to do is saying, look, you should be able to constrain your problem. You should be able to put in some assumptions and only come up with solutions that exist in this space. And basically, you should be able to figure out, even if your Fourier recon or your parallel imaging recon, if it says that this is a possible solution, you know it's not a solution. So you should drive your solution away from here into this space. Okay, so that's what compressed sensing and deep learning are going to be doing. Okay, and because of that, they are able to do things that are sort of almost look magical. Okay, because they basically, what you're adding to the sauce now is you're adding prior assumptions. Okay, and for those of you, are there any Bayesians in the audience or online? Anyone who's a real Bayesian? It's basically Bayesian, right? So Bayesian is saying there's always prior assumptions, right? So if, up to now, we've been using a uniform assumption, right? Anything is possible, right? But if anything is possible, I have to account for a lot of possibilities. But if I put a strong prior and say, well, only these images are possible, then I don't need as much data, right, to estimate parameters. So essentially, you can consider what we're doing is we're moving you from non-Bayesian to Bayesian, okay? So deep learning is a sort of like the ultimate Bayesian, right? Because deep learning the training is essentially you're coming up with your prior distribution, okay? Okay. So let's look at compressed sensing. So compressed sensing has a very interesting history. Once again, it was the first paper on that applied to MRI was by Mickey Lustig when he was a grad student at Stanford. Again, in science, a lot of the sort of the advances come from intersection of two fields. So there were some really brilliant statisticians at Stanford and Berkeley, David Donahoe and Emmanuel Candice, who came up with these theoretical results showing that you could do this. And so Mickey was the first to apply to MRI and has gone on to do lots of other cool stuff. But oftentimes, you know, if you can just find really smart people and take their solutions and apply it to what you're doing, that can sort of advance your field. Okay, so this is one case where this theory was adapted to MRI. And so here's the idea that, let's say you have your Shep-Logan phantom, right? And you take its Fourier transform, you get this. Now you downsample it. And so and here, notice I'm just randomly sampling it. Okay, so that's one of the keys behind compressed sensing is I just randomly sample this thing. Okay. So if I take this random sampling in K-space and do the minimum norm solution, which we talked about, I would get this. So that looks terrible, right? But if I do compressed sensing, I get that. Okay. So from the same data, I can either do a bad job or I can do a really good job. Okay. And so the whole idea is, what is compressed sensing doing? So we're just going to give you sort of a flavor of that. We can't really go into the details given, you know, the constraints on this course, but let me give you a constraint, the sort of the understanding behind it. So we're going to change the solution where this is one way of phrasing the equation. I'll show you another way, but essentially there's something called data consistency. So S is a signal I measure, M hat is my estimate, and E is the encoding matrix. So data consistency is I just want to make, this is what I predict the measurement should be. This is what the measurement was. I want to make that difference small, right? That's just saying whatever I predict should explain my data. So that's data consistency. Okay, if I just did that, and that's just solving essentially the least squares problem, right? And as we saw, if I do that, I don't get a very good image, right? So here I had another constraint. I want to do this, but I want to go away from that aliased image to a better solution. And that better solution, instead of minimizing the norm, which would be minimizing M hat, so typically I would minimize M hat, the 2 norm of M hat. That's what the least squares, the minimum norm solution would be. So this is a minimum norm. That's the solution that gives me aliasing, okay? I apply a different one where now I'm minimizing the L1 norm of phi times M hat. Okay, so what does this mean? So L1 norm, for those of you may already know it, is essentially just you take the absolute value of every element and you just add up those absolute values. So what it does is the L1 norm, if I minimize it, I enforce sparsity. Okay, so things that minimize the L1 norm tend to be things where we don't have many coefficients. most things are 0 and you just have a few non-zero coefficients. That's what's going to minimize the L1 norm. Okay, so here phi is chosen to be a sparsifying transform. So I want to find some transform that takes m hat, puts it in a domain where the biological images will tend to be if it's actually a biological image, it will, in that domain, it will tend to have a few non-zero coefficients, and a lot of the coefficients will just be noise. Okay, so that's what the sparsifying transform is. And it turns out that a really good sparsifying transform, which is the basis of, you know, why you can do image compression for the internet, is the wavelet transform, or things similar to wavelets. Okay, so wavelets are really good at taking an image and converting it into a domain where most coefficients are just noise and just have a few coefficients that really matter. So that's what this looks like. So for example, here's an image, and here you basically need every voxel in this image, right, to represent your image. If I take the wavelet transform, you can sort of see here, a lot of these are like 0, so I don't need as many coefficients. So this is what's called a sparsifying transform. Okay, so essentially what it's saying is, pick the solution here, which is going to give me the sparsest possible representation in wavelet space, and that's what I want. Okay, and because the thing with incoherent artifacts, guess what? If I put that in the wavelet transform, it's going to make a lot of these bigger. Okay, things that are very small for a real image, once I add noise, these are all going to go up. Okay, so that's not going to be the best solution. So it's driving my solution to something that I think is more biologically relevant. Okay, so basically, and this is for on the pre-lecture quiz, one of the questions is going to be about compressed sensing. And so the intuition you want to have is the more structure there is in an image, the more easily you can compress it, right? And so compressed sensing should work out. The more noise you have in an image, then it's going to be harder to compress it, right? Because it's essentially, you know, you've got it's hard to sparsify noise, right? The noise, random noise is just hard to represent with a limited number of coefficients. So when you're looking at your options on that pre-lecture question, you want to think about which of these images has the most structure and the least noise, okay? And that sort of will tend to give you the right intuition. Okay, so anyways, let's look at some examples of compressed sensing. So this is if you acquire all of K-space. Okay, so this is an angiograph showing the vessels in your leg. So one way you can go faster, as we talked about, is just don't acquire the high spatial frequencies. So you could go faster, but now you have much lower resolution. So you've really lost all this detail here, right? So like this little thing going here, you can't see that anymore, right? And this one, you've totally lost this, right? Almost, okay. And all this beautiful structure here, like the fact that there's all this stuff here, you can't see it on the low resolution image, okay? Now let's just say you did your best linear reconstruction, okay, like a minimum norm estimate. It's okay, but it's pretty noisy and you still aren't seeing a lot of the details. You still lost a lot of the details, okay? And a lot of that's because you've amplified your noise and there's aliasing, okay? So the idea is when we undersample every other line, we get this very structured aliasing, right? When we sample randomly, okay, the aliasing becomes like adding noise, okay? So it's like you imagine you have all these replicas, but they're added at random things, and so it appears as noise. And so that's why you're sort of seeing this really high noise level everywhere, okay? Now I go to the compressed sensing, and you can sort of see we're doing a pretty good job of reconstructing the original image, okay? Because we put that constraint on is I want an image that can be sparse in, say, the wavelet domain, okay? And you can sort of see here that here 1A and D are from the full Nyquist, okay, full Fourier. This is from 3 to 4-fold acceleration, and this is from 6 and 4-fold acceleration. So here we're going, I think, 12 times as fast, and this is 24 times as fast. So it's a huge gain in how fast you can go. And you can sort of see that to first order, these look all pretty good. Okay. So compressed sensing is not, I wouldn't say it's standard on all systems, but you will tend to see it. It is coming into play in certain applications. So that brings us, so yeah, so we'll spend the last 15 minutes on deep learning, and I think that'll take us through the end of today's lecture. Okay, so what is deep learning? Well, deep learning is basically, as you all know, it's basically you just train the algorithm. You don't have to spend time learning about Fourier transforms or all the stuff we've spent 5 or 6 lectures talking about. You just bring up, your Python script and, whatever, your favorite, Keras or whatever, and you just type literally 5 lines and you're done. Okay. That's only because a lot of smart people have done like years of work to make it so simple that you can just, I've had high school students do projects, and that we've published in like Proceedings of National Academy of Sciences because, they watched Coursera, they learned how to program Keras, and, they actually got it up and running in like a summer. Okay. So, the Google and all those, Amazon, they've made it so that deep learning is so easy to do. Okay. So we can take advantage of that. And so here, so essentially, actually, this is actually from the paper. This is the TensorFlow Keras code that this paper uses to generate the results that I'm going to show you. So literally, it's just that much code. Okay. And so this is what it can do. So we're going to just look at the results, and then my only goal in this lecture is to give you a sense of what deep learning is doing and why it might be working the way it's working. Okay. So these are the reference images. And so the encoding is just showing what the case for trajectories were. So here we're doing projections, radon projections like CT. We're just going out in case space like that. Here we're doing a spiral. So not the square spiral, but sort of a Archimedean spiral. Here we're just undersampling, like compressed sensing, just taking random images. And here we've misaligned the Fourier transform. So instead of getting line by line, it's like you had a mistake. You acquired here, and then you acquired this line, and you sort of offset your lines, and you just had like, you made mistakes. Okay. So AutoMap is our deep learning network, and this was Nature paper in 2018. And you can sort of see AutoMap does a pretty good job of reconstructing all of those. Whereas look here, if I misalign the Fourier data and just reconstruct it without knowing that, this is what I get. Okay. AutoMap doesn't know that we did this. AutoMap takes the data, this data, and gives you that. Because basically it says, well, this can't be a solution because this wasn't in my training set. So it moves you away from that solution into a solution that is most consistent with the data and also consistent with the training data. Okay. Here's compressed sensing, and it does fairly similar to compressed sensing. Here is conventional AutoMap. This is conventional, like this is basically your CT-like projection. Some of you, I think, maybe did some algebraic reconstruction technique. So this is essentially a CT-like reconstruction. AutoMap does way better. Okay. And the cool thing about AutoMap, it wasn't, I think if I remember correctly, it wasn't even trained on MRI data. It was just trained on like ImageNet. Okay. And then here, you're doing what's called a non-uniform FFT, and you do a pretty good job. But here, this algorithm probably took, at least 10 smart people, like 20 years to develop. Okay, just the theory behind this and all the algorithms, right? And so it's replaced with 5 lines of code, and AutoMap can just do it with the training. All right. And this also takes a lot. These algorithms take a long time to do. Okay. This one executes. The cool thing about deep learning is once you've done the training, you just have these coefficients, and it's very fast to do, right? It's a forward calculation. Okay. These algorithms involve a lot of iterative, highly computational computations. Okay, so let's look at what it does. So AutoMap is one form of deep learning for MRI. It actually just takes your data right off the MRI system, and it has a few what are called fully connected networks, which basically just take all the data and just combine them in different ways. So here, you're still sort of in the Fourier domain, really, right? And then you're going to sort of these convolutional networks, and then some what's called deconvolution, and you get your image. And you notice that the basis functions or the features it's finding in your data of what corresponds to good images, you notice these are some of the features it finds in those later layers. And you can sort of see those looks like Fourier basis functions, right? right? It's very similar to the stripy patterns we showed. So basically what it means is if you train k-space, if you give your algorithm k-space data and tell it, I want to reconstruct real images, it will figure out the transform between that k-space data and Fourier component. So it actually figures out the Fourier transform on its own, okay, which is pretty cool. This is just showing that if you compare, this is the ground truth. This is 4x4 acceleration. So I've accelerated 4 times in both dimensions. Since this is just sort of simulation, you can do that. And so this is AutoMap, and this is the sense recon that we talked about. And this is the root mean squared error. So here you have a 10% error, here you're down to 6% error. Okay, so AutoMap is already outperforming the state of the art there. And it does really well in low signal to noise ratio things. So here, if I drop the SNR down to, let's see, SNR 13.2 reference. Okay, so I think here they just added noise, and you're sort of seeing AutoMap still gives you a really good image, whereas conventional imaging is really affected by the noise. Okay, and here again, AutoMap, because basically AutoMap, the deep learning knows, well, noise isn't really biological, like random noise isn't biological. So I'm going to move away from solutions that have random noise and go to solutions that don't have noise. So it turns out deep learning is actually really good for removing noise too. Okay. Okay, so let me just give you an overview of how people, this is still an active area, but let's just look at here, some of the trade-offs here. There's some really good articles here that are sort of cited here as well. And there's there was a conference on this, so you can look here. But here's the idea that with conventional imaging, imaging time is long, right? But reconstruction time is relatively short, right? Because you're just doing Fourier transforms. And people have figured out over the last half century how to do Fourier transforms very quickly, or inverse transforms very quickly, okay? FFT, right? Compressed sensing we can use to make the imaging time much shorter. But the reconstruction time is really, really long. You're solving this iterative solution. You're looking for the solution and iterating and iterating and iterating, and you're searching through the space, okay? Machine learning decreases both imaging time and recon time because the training has already done the pre-search of the space, okay? And you just get the weights. And so then you just apply the weights, and that's very fast to do, okay? So there's a couple ways you can do it. Image domain learning is here. You can actually still reconstruct your image. So let's say we took this and we can reconstruct an image that had aliasing in it, or okay. Then you let your deep neural network figure out what to do with that. Basically, you reconstruct it and you get a crappy image. You put that crappy image into the deep network and let it figure out how to make it better. So that's one approach. The other approach is what AutoMap does is domain transfer learning. You go directly from k-space to the image, okay? There's hybrid domains where you do a little bit of both. You say, okay, I can have one path that sort of, I'll do sort of, let's see, what is this doing? Okay, one case, it's doing the reconstruction and then doing a deep neural network and then letting the deep neural network fix this. But it's also giving you sort of this like a feed forward, right? A skip connection where it's giving you some of this information at the end to help you do a better job. Okay, so all the things that those of you who've done deep learning, all those tricks people are playing around with too, like how do you introduce additional side information? And then there's also a sensor domain where actually you use the deep neural network to clean up your case space itself. Okay, you say, okay, here's my case space, but this case space has a lot of problems with it. Deep learning network, clean up my case space data, so then I can just inverse FFT it and get a good image. Okay, so these are the different approaches people are trying. So basically, here's the intuition, which we'll be talking about. Remember this corresponds to undersampling, right? I have more equations, less equations than unknowns. And so I'm going to get infinitely many solutions, right? But of all these infinitely many solutions, a lot of them are not good solutions, right? So I want to pick the solution that looks the best, right? And in fact, this is, all of these are bad solutions, right? So the job of my recon is how do I go from this universe of infinitely many solutions and pick the solution that's most consistent with what my training data sets do. So this is essentially can I learn to go, and here's the case where we did the bad recon, can I actually let the deep learning network go from this directly to this? Okay, so that's one way of doing deep learning. Okay. And as you can sort of see, what it's looking for is looking for a solution that lies on what's called an image manifold. Okay. And what does that mean? Well, it means that an image manifold, as you can sort of think about, is sort of like a low dimensional space, right? It doesn't have to be Cartesian. It's locally Cartesian, but it can be sort of globally sort of wonky in shape, okay? The deep learning is trying to say, okay, all my solutions must lie on some space, a low dimensional space. And so essentially, I'm going to drive from a bad solution and drive it to something that lies on a good solution manifold. All right. The other thing that deep learning does, and also as I was updating these slides, there's some actually nice books that have just come out. So those of you who want to go more into depth, these are, this guy's done a lot of stuff to advance how to apply deep learning, not just for MR. This book actually talks about MR, CT, ultrasound. So for those of you interested in this area, I think this is a good place to start. This just came out this year, okay? So that's how, I mean, this field is only about 5 years old, okay? So one of the things that this guy figured out, which was why deep learning works so well, which is this. I think most of you know that in deep neural networks, there are these nonlinearities, right? Typically RELUs, the rectified linearities, right? And so they basically go from everything we've done up to now has been very linear, right? We're like addition, subtraction, multiplication, everything's linear. There's nothing nonlinear. And so you're sort of constrained as to what you can do. Compressed sensing is the first time we're seeing some nonlinearities, right? Where we're imposing constraint on, say, the L1 norm. The deep learning takes it even further. It basically says, I'm going to use these nonlinearities to sort of split my solution into different spaces. So this is what this partitioning is. It says, if I get an image of a head, I use the deep learning. It says, oh, well, if it's a head, it should look like this. And I'm going to use these sort of coefficients. And if it's like, I guess that's a leg. Okay. If it's a leg, that's a different kind of image. So I'm going to use a different set of coefficients. So it's actually smarter. It sort of says, it does this splitting of your data into telling it, well, what's the best solution space to do your operation in? So that's where something that the geometry of deep learning, these nonlinearities actually help you. And essentially, you're driving yourself into the space of solutions that you want. Okay. So let's just end with a few examples of how deep learning is already in product now. Okay. So the manufacturers, once they saw that, were very fast to get it into the product. And so this is basically, this is from GE. This is the Air Recon DL that is sort of like AutoMap, where it actually goes directly onto the K-space data. And essentially, yeah, I'm sure. Let me see, IFFT. Sorry, I don't remember exactly what this did, but this is actually a better example here. So here, if we look at conventional imaging, okay, as I change the resolution size, you sort of see things getting blurred out, okay? And this is sort of that Gibbs ringing type artifact we talked about, right? Where things start getting blurred out as we reduce the resolution. But look at this, the deep learning, even as I make those voxels bigger, it actually keeps that resolution, okay? So if somehow it knows that the images should have that resolution, so it keeps that resolution, okay? Here is just showing deep learning to go faster, okay? So these images were acquired in either 127 seconds or 15 seconds. These two, let's see, the cardiac images, right? Let's see. A and B. Okay, this is 127 seconds and 15 seconds. This reduced it to 61 seconds, 11 seconds. So not quite a factor of 2, but essentially showing, and you can argue that this deep learning image is arguably a lot better than the classical recon, right? It's not only faster, but it seems to be getting you more information. Okay, so deep learning is actually sort of working much better than anyone thought it would. Here, they've the same scan time, but you can sort of see here they're resolving the structures a bit better, I guess. Let's see. Time of acquisition is the same. Okay. Here they've also just showing you're sourcing more detail with the deep learning. And here they reduce the scan time, and you can sort of see 23% reduction in scan time, but the image quality is still pretty good. And you can argue that this is even slightly better. You're seeing more detail here than over here. Okay. Okay, so that's all we're going to talk about for deep learning. We're at the end of the hour. So any questions before? I guess I'll talk a little bit about project 2, right? Okay. Okay, any questions online? I guess not. Okay, so I'm going to just show one slide on project 2, and I'll talk a little bit about this. So this is the, everyone can see this? This is a histogram of scores. So the mean score was 80, the median was 78.5, so they're all around here. And so there's the range of scores, and there's maybe 2 what we call outliers, okay? So I would say, this is a fairly tight distribution. So I'll just say a few words. So first of all, for anyone concerned about grades, this is a graduate course, so we do curve the grading. And so, it will be based on the grading will be based on a curve. And typically, since it's a graduate class, it's typically around B+, A- centered. Okay. So, so hopefully that alleviates any concerns about grades. The project, I just was able to coordinate with Professor McVeigh this morning, so we will be posting the final grades later today with some comments. I'm sort of right now consolidating our comments to be more readable. So what you're seeing is sort of the overall consensus feedback from both instructors. We've done our best to sort of, if there's any discrepancies, to sort of come to a consensus score. The comments will be relatively brief. They'll be mostly suggestions. Take them as more suggestions like, okay, if you didn't do as well as you hope to do in project 1, here's some guidance that things to look out for project 2. I mean, everyone did very well, but there are just some things consistently where that are sort of addressed in the project 2 description, but essentially just make sure you don't, for project 2, it is advisable not to spend too much time just regurgitating things that were already presented in course, right? Basically treat every minute wisely, okay? So don't waste your minutes, okay? If you say something, if you make any claims, just make sure you check that it's valid, it's supported by what you presented already. So some of the comments would be, for both Professor McVeigh, for some of the projects, we're like, we're not really sure that's correct, okay? And it's not like we're going to spend hours and hours debugging what's incorrect, but just, given that we have between the two of us, over, I don't know how many decades of experience, we sort of know what sounds right. And so so do your best to make your project minutes, use them wisely, and just make sure you check whatever you say. And I think, I certainly want to encourage you. I mean, I think this year in particular, I'm not sure that the class has really taken full advantage of instructor office hours or instructor help as compared to previous years. So I think maybe for project 2, we're here to help you, and if you don't ask us, it's really hard for us to help you. I know in past years, typically the students have been a little more sort of taking advantage of assistance, and their projects have tended to benefit from that. So realize that, the lectures, the office hours, we're here to support your learning, but we can't really do that if you're not here or you don't ask questions. Okay. So, so hopefully later today, everything will be posted. If you have any questions about your score or the comments, send an email to both Professor McVeigh and myself. And we will take a look at that and get back to you. Okay, or you can also ask us in person. All right, anything else? Okay, great. So I'm going to stop recording for now. I'm here to answer any questions you may have.